begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for all the students that are here. And I just ask you to bless this class, Lord. In your name I pray. Amen. So yes, we had a quiz. It's 56 degrees, a constructible angle. And we learned in the last class that it's constructible only if it's a multiple of 3. So, sorry.
It's a multiple of 3?
Multiple of 3, yeah.
Wow.
Could have gone either way, but, you know, what can I tell you? Now, so the next topic here, section 13.4. All right. So here we go. If I can erase. Oh, and you know, it just seems right that we should top hat again. Huh. 2941. Oh, that was the one last time. 7716. Zero 0525. Okay, I think it's enough. All right.
I tried 1.5.
Wow.
I failed top hat. I just failed top hat.
You failed top hat. Now you're never going to make it at meaningless tasks in life. Unfortunately, in the modern world, that's most of what we do.
My attendance went up a percent.
Section 13.4.
I'm sure mine is abysmal now.
I'm just kidding. I'm just kidding. All right.
Yours is probably horrible. You need 6 classes.
Splitting fields and algebraic closures. So I've talked a fair amount about how we can, take a base field, right, and go away, stupid thing. How we can take a base field and we can make it larger by looking at an extension, right? And we talked a lot about what does it mean for the extension to be an algebraic extension, and how finite extensions are necessarily algebraic, right? But is every algebraic extension finite? I think the answer to that is no, but I'm forgetting the counterexample. There's a nuance I think I failed to bring out in the previous section. Well, theorem 17 said an extension K over F is finite if and only if K is generated by a finite number of algebraic elements over F. All right, we looked at that. We had, definition K over F is finitely generated if and only if there are, if there are elements alpha 1 through alpha K such that K is F adjoin those elements. Okay. This definition, I suppose. Come on. And we had corollary 13 said that if the extension K over F is finite, then it's algebraic, right? And he has a remark after that. He says, we'll prove below a sort of converse to this result, which is theorem 17. But note, there are infinite algebraic extensions. We'll have an example of that later. So the literal converse of this corollary is not true. So if I have said that inadvertently, that it's algebraic if and only if it's finite, like that's not true. There is an interrelation, but it's not quite that simple. Certainly, if the extension is finite, then it's algebraic, but there do exist infinite algebraic extensions. Yeah. Okay. Question? No? So the next section, just wanted to say a word about that. So now we're in 13.4 here. The question is, if we're given a polynomial over a field, right, then there exists an extension field for which that polynomial has a 0, right? And so what's a splitting field? The extension field K over F is called a splitting field. For f of x in f of x. I should say for f of x in f of x. There you go. If f of x, sorry, that's horrible, factors into linear factors in k of x and f of x does not factor in any proper subfield of K containing F. All right, so I have a remark here in my notes. If f of x has degree n, then f of x has at most n roots, counting multiplicities in f. Furthermore, f of x factors in f of x if and only if f of x has n roots, counting multiplicity in the field, right? So do I need to write that down, or does that make sense, what I just said? So remark, f of x degree n in f of x is split linear, meaning f of x equals to, say some constant a times x minus r1, x minus r2, x minus rn for r1, r2, rn in the field, right? If and only if, there exists r1, r2, rn in the field, such that what? F of rj is equal to 0 for all j. So we can factor it into a product of linear factors in a given field only if we have, of course, 0 roots possibly repeated, right? This is the factor theorem, remember? Now, the issue of multiplicity is dealt with in section 13.5. We'll get back to that, okay? But at the moment, we just want to talk about this idea of a splitting field. And so theorem 25 says the following: for any field f and f of x in polynomials over f, right? There exists extension K over F, which is a splitting field. For f of x. So the proof is by induction on degree. So we're going to prove this by induction on the degree of f of x. All right? So we start with, let's call that degree n. Right? If n equals 1, then what are we looking at? F of x equals to mx plus b, right? So what's at 0? F of minus b over m equals to 0. So if the degree is 1, that assumes what? N is what? I mean m, rather. M as in mommy, not n as in nanu nanu. What's that? Not 0, right? Degree 1. So that's important because otherwise division by m would be troublesome. But it's not because it's not 0. And there you go. That shows that in fact, what's the splitting field for f? I mean, the splitting field is f itself, right? Any linear polynomial over a field is already a linear factor over the field. Okay, there's not much to prove there, but there it is. So, I mean, I guess, well, I don't know, do you really need, I mean, it's debatable. Okay, so I think here I've fallen into a trap, which is I've said something that doesn't even need to be said, right? Because our definition of splitting field was what? F of x factors into linear factors in k of x, right? So do I need to show that it has a 0? I don't, right? I mean, this is not necessary, what I just wrote. What can we do? If n equals 1, then f of x is a linear factor, which is therefore already factored into a linear factors, which means that f is its own splitting field. I don't actually need this jibber-jabber here. I'm really including that more as a point of connecting with my remark. All right, so it's not, I would say it's not really needed for the proof. Okay, then, suppose f of x splits in some extension k, all right, for any f of x with degree f of x equal to n. Okay, so then what I say is if f of x I've messed it up. Degree what? This is supposed to be n, but I'm supposed to put n minus 1 here. Can't follow my own notes. And I still have messed it up. I actually want to do what? not weak induction, but strong induction. So I should say, suppose f of x splits some extension k for any f of x with degree, at most degree n minus 1. So then I want to consider f of x of degree. If f of x has degree n, right? Then I say if f of x has only linear irreducible factors, is already split linear. So this notation is this split linear is a nice terminology. I don't think Dummett and Foote uses this terminology, but it's helpful. What that means is that the polynomial is written as a product of linear factors, possibly repeated. Split linear. So if f of x is split linear, what does that mean? That means that it's already split, which says that the extension field we can use is, just like my base case, k equals f itself, right? F is its own splitting field in this stupid case. All right. Otherwise, f of x has at least one irreducible factor of degree what? 2 or more. How do I know that f of x has irreducible factors, by the way? How do I know that? What's that? It's not already in linear factors, right? But how do I know there are factors to start with? Like, how do I know I can take f of x, a polynomial, and break it into a product of irreducible factors? Remember, this is all in the backdrop. What's our context? Polynomials over a field. We proved it's a unique factorization domain. So we're always using that, right? So we know that there exists we can write f of x as a product of irreducible factors, right? That's the fact f of x is UFD. So then what? Then, what is it? No, okay. I say then, there exists E1 over F such that alpha is an element of E1 with and I gave this irreducible factor a name. Let's call this irreducible factor P of x, okay? So with P of alpha equal to 0. And so f of x is equal to what? X minus alpha times g of x for some g of x in where? In E1 of x, yeah? And what's the degree of g of x? N minus 1. So we've taken f, we've extended to E1, right? we have f extended to E1, and E1 extends to K by induction. And in this K, g of x is split linear. Right, so we picked off a n minus 1 degree polynomial over a field. And I believe our induction step was what? That oh, wait a minute. Flag on the play here. I say it splits in E by the induction hypothesis, hence g of x is a product. Well, I've called, instead of K, I put E here, but sorry, I'm too close to the board. Is that a reasonable application of the induction hypothesis?
Wait, where did E come from? And what happened to K?
Oh, E is the, I'm using the induction hypothesis to say that there exists this E in which the g of x splits.
And that's not K.
That's what
Oh, I mean, well, I'm just calling the K E, but
So I left it as K, is that still right?
it's fine, yeah. We can leave it as K. I'm sorry, I don't think this is wrong. I just have this sense of like something is missing. And I can't put my finger on it at the moment. What's bothering me?
So f of x splits in K if its degree is less than or equal to n minus 1. And then you just managed to make f of x, which had degree n, equal to x minus alpha times g of x. And
Yeah.
because of that, g of x necessarily is a minus 1, and so that's in K, right?
That's
That seems to
so the story goes. I mean, it makes sense to me that if g of x is split, I mean, if g of x is split linear, it follows that f of x is split linear because like if linear times linear is still product of linear things, right? What's bothering me is that the g of x is a polynomial in the extension, but it seems like the induction hypothesis was stated for polynomials in where? I mean, f of x and f of x, right? So I'm missing something here. I mean, like, it seems to me like g of x is in the wrong spot.
No, but you are assuming that it's true for all things up to n minus 1, which is saying that you're assuming that there exists an extension that g of x would split in.
Ah. Okay. Okay. Sorry. Let me not be an idiot. Let's move on here. Okay, so the question then is, what's the splitting field? Like, for a given example, are we to a splitting field or not, you know? And so here's some examples. Like, you know, our basic example. You know, if we look at x squared minus 2 as q adjoining square root of 2 as splitting field, right? Now, I guess it depends on the context, right? X squared minus 2 where? As a polynomial with rational coefficients, right? And why is that a splitting field? Because in here, you have x minus the square root of 2 and x plus the square root of 2, both elements of what? You know, polynomials with root 2 as coefficients, right? So in that extension, q adjoin the square root of 2, the polynomial x squared minus 2 splits into a product of linear factors, right? Another example, he looks at x squared minus 2 times x squared minus 3 over q. This is splits where you take the square root of 2, you join the square root of 3, right? We proved that that's a degree 4 extension, I think, last class. And so in here, right, we have x squared minus 2 times x squared minus 3 is x minus root 2, x plus root 2, x minus root 3, x plus root 3. All right. Drawing a field diagram for this example for some reason. I wonder why I'm doing that. Let's draw it. So what do we know so far? Splitting fields exist, right? The question is, what is it for a given polynomial? Like, how far do you have to go before you get it? For a given case, it may be like not obvious whether or not your given field already is a splitting field, right? Determining whether or not a polynomial has real roots is not entirely a trivial matter, is it? If you have a real polynomial. So here are the subfields of this one. There are 3 subfields, right? And these are all degree 2 extensions to get up to there, and they're all degree 2 extensions over the rationals. So we have this diagram for the splitting field and the subfields of that splitting field over the rationals. Yeah. Another example. Let's see here, x to the 4th plus 4. I point out that you can factor that. Everybody's doing it, right? X squared plus 2x plus 2 times x squared minus 2x plus 2. Yeah, obviously. Which is x plus 1 quantity squared plus 1 and x minus 1 quantity squared plus 1, which is, by the way, x plus 1 minus I times x plus 1 plus I times x minus 1 plus I times x, rather minus I times x minus 1 plus I. And, honestly, if you want to know where this example comes from, I think the more honest answer to that is if we look at x to the 4th equal to minus 4, that says that x is an element of the 4th roots of minus 4. And, what is that? That means x is an element of the set, like the principal 4th root of minus 4, I times the principal 4th root of minus 4, I squared times the principal root of minus 4, or I cubed times the principal root of minus 4. Because that's how to solve the equation x to the 4th equals minus 4. We look at when you find the principal solution and then you multiply by the 4th root of unity, which is I. The principal 4th root of unity, e to the 2 pi I over 4 is e to the 2 pi I, e to the pi I over 2, which is just I. Now here, to calculate the 4th root of minus 4, you just convert to, that's really the 4th root of 4 times e to the pi I. See, pi I is minus 1. E to the pi I is minus 1, because that's cosine of pi plus I sine of pi, which is just minus 1. And once you have it in polar form, this is really very simple how that works. It's the 4th root of 4, all right? And then e to the pi I over 4. But what is the 4th root of 4 times e to the pi I over 4? It is the 2 to the 2 over 4 times the, 1 over root 2 plus 1 over root 2, I over root 2 rather, which is, well, nothing more than 1 plus I. And so if you look at what this example is, it's really, I mean, I will tell you how I make up such examples. It's not because I'm just like, oh, I know how to factor x to the 4th plus 4 like this. I'm not Sprano. I mean, Sprano would just do that, right? Because he has that kind of beast algebra strength, and that's good. But right here, that's x minus the 4th root. And then if you look at the other three, they're obtained by multiplying this by I, or minus 1, or minus I, to get the other. Those are all zeros of the equation x to the 4th plus 4. Anyway, I digress a little bit, but I think you guys are in need of some of these comments, right? Okay, so the larger question here is, if x to the 4th plus 4 is a polynomial in Q of x, then what's the splitting field? Can you guys tell me? Q adjoin I. Right. Now, I think Bethany's right, but what should your base thought be? Like, the base thought is not that. The base thought is that the splitting field, if I'll call it K for a second, would be Q adjoin all the roots, right? 1 plus I, what are they? 1 minus I, minus 1 plus I, minus 1 minus I, right? Like that would be the splitting field that I would just, my knee-jerk, you take the field you're given, you adjoin all the roots. That's the splitting field. But then the question is, what's the most minimalistic description of it, right? Like, can you pare it down? And the answer is absolutely. Because what Bethany mentioned, this guy, that has all of these other bells and whistles, right? Q has 1 in it. So Q adjoin I has 1 plus I. It has 1 minus I. It has minus 1 plus I. It has minus 1 minus I. It has all of these guys. So in fact, yes, Q adjoin I is the splitting field for this polynomial.
So like, neither of those are wrong ways to express it, except one of them is super redundant.
Yes, one of them, thank you for reminding me to be careful how I word my next test. Yes, like significant partial credit in blue, me being happy in red, right? But yes. But they are the same thing, right? They are the same thing. As a set. Conceptually, they're different, though, right? Uh-oh. What the what? What? How? How did... What? How? No. My notes have this annoying green comment. It seems x to the fourth plus 1 has the extension field q is I, comma, square root of 2. Square root of 2? What do you mean square root of 2? There's no square root of 2 in here.
Wait, but you said x to the fourth plus 1. You did 4.
This has x to the fourth. Oh. Thank you. You're helping me not to hate myself today. It's good. So this is just a remark. X to the fourth plus 1 has the splitting field k equals to q adjoin I and root 2, apparently. So x to the fourth plus 1 factors how? I think. So like, so x squared minus e to the pi I over 2 times x squared minus I squared e to the pi I over 2. That's right. X squared minus I.
Yeah, because you get -1 from the i's, and then, but e to the pi I is -1.
Cool. So yeah, I mean, yeah. But then but where's this root 2 coming from? It's because e to the pi I over 4 is what? It's 1 over root 2 plus I over root 2. Because this is, cosine pi over 4 plus I sine pi over 4. So that's why I'm saying that x to the fourth plus 1 has q adjoin I and root 2 as a splitting field. In contrast, if you look at x to the fourth minus 1, that splits in q adjoin I. All right? Proposition 26, what's it say? A splitting field of degree n polynomial is over f is at most n over f. So the proof is very simple. K is equal to f adjoin alpha 1, alpha 2, alpha n, right? Where f of alpha j is equal to 0 for j equals to 1, 2, n. So remember what we learned about the extension by finitely many elements? The degree of this composite extension, it's at most a product of the degrees of each extension, right? What I'm trying to say is f adjoin alpha j over f is at what is what? The degree of this is less than or equal to n. Oh, that doesn't, what I'm arguing right now doesn't get me n factorial. What's it get me? What I'm arguing at the moment would just get me n to the n. We can do better than that. So I think I actually need to kind of think through it. So, okay, so oh, phooey. SGA, you say, huh? Doesn't really matter, though, right?
It's for the math club, so it's for math club, so it does.
I already got my free bowling for the year. I don't care about you guys now. Thanks for the free bowling, by the way. No. Oh.
You still have another year stuck with us. I need to.
I have to think about like it's something like this. We take f, we extend to f adjoin alpha 1, right? And then we extend that to f adjoin alpha 1 adjoin alpha 2, you know? So, I mean, we're starting with f of x down here, right? And by the time we're up to the adjoin alpha 1, we already have f of x equal to what? X minus alpha 1 times g of x, where g is degree n minus 1, right? So, so it follows that this alpha 2, the thing we're adjoining, right? I think we can assume alpha 1 not equal to alpha 2. There's some nuance in the proof I'm skipping over at the moment, but suppose alpha 2 is not equal to alpha 1, right? If alpha 2 is not equal to alpha 1, that means that g of alpha 2 must be what? If the next thing up is going to have alpha 2 as a 0, we'd need that g of alpha 2 is equal to 0, which would mean that alpha 2 is the 0 of an n minus 1 degree polynomial. So this extension would be less than or equal to n. This one would be less than or equal to n minus 1. And you just keep doing this process until you eventually get up to f adjoin all your alphas. But by the time you get to the last one, you've only got one thing left to adjoin, so it has at most degree. I mean, by the time you get down to the last one, you're degree 1. Anyway, if you sort through this, you can see why you have this n factorial, right? Because you get extend by n, and then n minus 1, n minus 2, and 3 times 2 times 1. So, so I'm sorry, I haven't quite done the proof justice at the moment, but you can see you can see it already working in our examples, right? I mean, in fact, it's not usually even the case that you need an n factorial degree extension to split it, do you? I mean, x to the 4th, did we need degree 4 extension here? Oh, wait a minute. This is a degree 4 extension. Because here's my intuition for that. I and root 2 are independent. Just like 2 and 3 are independent, and we got a degree 4 extension from these two quadratic elements. Both root 2 and root 3 are degree 2 over the rationals. I is the square root of minus 1. Don't look at it so differently. This is really the square root of minus 1 and the square root of 2. It's also a degree 4 extension. Oh, you were glaring because 4 factorial is not 4. Good, very good. Yeah, this is not my example. This is not the example I'm looking for the n factorial actually being realized for a splitting field, right? I mean, degree 4 extension, not 24. Wait, what's 4 factorial? 12. It's 24? Okay. I doubt everything today. On the other hand, over here, what? Degree 2 extension, right? We already split this 4th degree. And of course, the stupid example would be when all the roots, when all the roots are already in your field, then it's already its own splitting field, right? So you don't even need an extension. What starts to get interesting is, trying to study what are the properties of splitting fields. I still haven't gotten to the really interesting example. But that's fine. We'll talk about this another day. So, man, this is the worst day for me to have 2 hours. I'm going so slow today. Oh, yeah. You can hit it.